Do a problem that I think is a little more interesting. Here we have an RLC circuit, and it is an RLC AC circuit. Right, our source here is 50 cosine omega t plus 30. Now, we haven't done any examples where we convert sources into phasors. So let me go ahead and quickly do that here. The idea is, if you have a voltage or a current and it's equal to some number cosine omega t plus theta, the phasor version of that is going to be just A angle theta. And the reason why is A cosine omega t plus theta, that is the real part of the number A cosine omega t plus theta plus J A sine omega t plus theta. And so what we're going to do is we're basically complexifying, we'll say complexifying or anti-realifying, whatever you want to call it. We're adding on this other term with sine here. We're adding it on with this J, and then when you combine them together by Euler's identity, this thing here becomes A e to the J omega t plus theta. And so that's fine. And then what we're going to do is we're going to go ahead and essentially leave the omega t out of it. And we're going to have this being the coefficient and e to the j omega t being the function. And so this over here, this part here, this is the phasor version of the voltage. So that's how we're going to convert it. Now, this only works if you have a cosine as your source. However, we saw in the earlier slide that you can convert sines into cosines using trig identities, and we'll see that in some of our later examples. Okay, so let's start over again here. So I'm going to go ahead and I'm going to write down the phasor version of my circuit. My new voltage source is going to be the phasor version of it. It's going to be 50 angle 30. My resistor is the same. All right, the impedance of a resistor is the same as the resistance. My inductor, we have the formula J omega L. And my omega is my frequency here, which we say F is 60 hertz, so it's going to be 2 pi times 60 times the L, which is 20 millihenries. And if I go ahead and multiply all that together, I'm going to get 7.53 J. Then I will need my impedance for my capacitor, and the formula for that is negative J over omega C. Omega again is 2 pi times 60, and my capacitance here is 50 microfarads. And then we put that in our calculator. And we are going to get negative 53.05 J. And so now we've got everything in terms of phasors. And what I want to do is I want to find the current. Well, we know that if you're trying to find the current through this circuit, and I won't write I of t, right? Phasor I in this case. Well, phasor I is just going to be the phasor V divided by the impedance. So I go ahead and do that here. So I would do phasor I is phasor voltage divided by the equivalent impedance. That would be 50 angle 30 divided by 25 plus 7.53 J minus 53.05 J. I will go ahead and simplify the bottom here. Combine the real and the imaginary. and I get a negative 45.52 J. And since I'm dividing things here, I'd like to write this into polar coordinates. So 25 minus 45.52 J, and use my calculator to go ahead and convert that into polar. I get 51.93 angle negative 61.2 degrees. And so then we know by our rules for dividing polar, we divide the front numbers and I get 0.96, and we subtract the angles. Now be careful here, 30 degrees minus a negative 60 degrees, you add them, you get 91.2. And if this is your phasor I, you can convert that back to your regular I by having this as the amplitude, and it always goes back to cosine omega t plus the angle, 91.2, and this is amps. And if you want to be even more accurate, we can put in what omega is, right? The F was 60, so 2 pi times that is going to be 120 pi. And so we just solved that with a little bit of algebra, but we got to completely skip any differential equations. There was no solving on auxiliary equation. There's no remembering the rules for if you have real, complex, imaginary, whatever roots you had. There was no looking for initial conditions, solving for constants. It's just a little bit of complex number algebra, and we get the final answer. So this is a really revolutionary technique for solving problems like this. And you're going to get plenty of practice in Chapter 9, Chapter 10 doing the same thing. So Chapter 9 was introducing this, converting into phasors. Chapter 10 is going to be solving circuit after circuit after circuit using these techniques, along with node voltage, mesh current, and all the other rules that we learned in the past.